So we started with neural networks last Tuesday, and we'll finish off now quickly the representation power, where we talked about what neural network functions can approximate. And then we'll talk a little bit about some activation functions that are popular until we then get to the main piece where we talk about how we train neural networks. Okay, so let's just finish off what we started last Tuesday. Last Tuesday we said there are really 2 points to neural networks. First of all, the neural network itself represents a function, and this function has many parameters, the weights and the bias terms. And if we hope that we can learn interesting things by using neural networks, then the hope is that these neural networks are powerful enough that they can represent a large class of functions. And we had started first to think about some particular approximations that were in what's called the L2 sense. So we're just interested in approximating a function within a bounded region such that the average L2 distance is small. And we did that, we stated first the theorem, and then we graphically showed why this should be true, why we can do this. And even with a neural network that has just one hidden layer. But this was kind of like approximate, and then we started to say that we can do this in an even stronger sense, namely infinity sense, in which we want to approximate a function such that the maximum difference between the approximation and the function is arbitrarily small. And right now we're just looking at this one-dimensional case. Okay, so what we had is that we said we need some smoothness. So we said, let's assume the function f is continuous. So we're just thinking of a function right now over some bounded domain, and it's a real valued function in one dimension. So this f of x, the x, the domain here is just one-dimensional, and so we might as well assume it's 0 and 1. And we said that any such function can be approximated by a piecewise linear function. So let's assume this is my function here. This is 0 and 1. Then there are several ways of how to approximate it, for example, by polynomials or by piecewise linear functions. So we have here a partition, similar to what we had for the Riemann sums. So once you give me an epsilon, which is how close you want to approximate it, then I can give you this partition. So this partition was, let's say, R0, R1, up to some Rm. And then within each partition, the function was just an affine function. Okay, so linear plus set off, right? So we can now approximate this function, and in each things it's piecewise linear, and it's also continuous, so meaning the end point of this part is the same as the point here. And so this means this function has the form, or the approximation of the function maybe, okay, has the form I is 1 to m. And so the approximation is that within each such partition or each such interval, so from Ri minus 1 up to Ri, it is just linear. Ai x plus bi. Okay, and so for suitable choices of the slopes and the set-offs here, we can achieve that, let me call this f tilde of x. We can achieve that f of x minus f tilde of x is smaller or equal than epsilon. And you can do this, so you first give me the epsilon, then I find the partition, and I find these slopes and the set-offs, the bias terms, such that this is true, right? And so now the question is, what does this have to do with a neural net? So we would like to now implement a function that has this shape in terms of a neural net. And remember last time it was suitable to use an activation function that was a sigmoid. And right now we would like to use
an activation function that is what's called ReLU. So it's a what's called rectified linear unit. Linear unit. And so this function looks very simple. It's this. It's 0 up to 0 and then has slope 1. Okay? So you can also write this down, of course, as sometimes just written as x plus, and we have seen that notation too. Okay, simply cuts off. It's just the line here, just the line x, but it cuts it off. Okay, as soon, and this is the same thing. We've also seen this already. The same thing as max of 0 and x. Okay, so instead of the sigmoid, we'll now be using this rectified linear unit. So this means that now at the nodes that we're having, the operation is still the same. We'll take the sum of all the inputs from the previous layer, right? And then we'll still have also some bias term here, right? So we have some bias term here. We take the sum. These are weights. There are weights here that we have. So that's all the same. But now, rather than applying the sigmoid function that we did beforehand, right? Recall the sigmoid function looked like this, right? Not a very good picture. Should be half. Even worse picture, okay? So, but this is a half here, right? So instead of applying the sigmoid function, we're applying this rectified linear unit. And we'll talk a little bit later on why sometimes. So this is not just an artificial example, something that's actually used quite often. And if you were in the exercise session, there was some talk about what's called the vanishing gradient problem. And we'll get back to it a little bit later. And so if you look at this function here, do you see that once it's fairly negative or fairly positive, the gradient or the derivative here becomes 0, and that becomes a problem when we do training. Here you still have a little bit this problem. You have this problem, but at least only in the negative part, versus here the gradient doesn't vanish. The derivative is always 1. And so we'll see how we can also still fix that. Okay, so this has something to do with the training phase. Good, so assume that we have, again, a standard one-layer linear network, right? So we have something very simple. We have D here is 1, because we are just in one dimension. Now we have a layer with some number of nodes. This is one layer of hidden nodes. So this is the hidden layer. And so it looks very simple, right? So we do a network. We want to represent now this function by something like this, and then we still can collect all these things, right? So there will still be weights. Like we can put here weights. We can put here bias terms. So everywhere here will be still bias term. And then we can still collect all these things. Okay, so that's the shape of the network that we want to use. And we want to show that if I have enough of these nodes in here, and I pick the proper weights and the proper biases, and potential also weights here, then we can represent any such function here, right? And then the math theorem already tells us that if we can implement this exactly, then we can approximate this function arbitrarily closely, right, in L infinity norm, because the maximum, this is for, this means for all, so this is true for all x in 0, 1. Plan clear? Okay, in the previous thing we had taking a function, taking the Riemann sum, then approximating. This was just a graphical proof of approximating these rectangles. Now we do it differently. We take a function, we approximate it by, by a piecewise linear function. And now what we want to do is implement this piecewise linear function exactly in terms of a neural net. Okay, but we're allowed to use these rectified linear units. So, it's quite easy. It will turn out it's very easy. We just have to slightly rewrite it. Okay, it turns out we can rewrite this in the following form. So there will be some other parameters which will be related to the parameters we have. So I claim that equivalently, I can write this whole thing in this way. Okay, so let's look. So this is again a sum. Forget about this is the first term. This is again a sum, right? And the sum simply has, there's some ai's in here. And then I have here the x minus some bi tilde, so there ai tilde, and then plus. Okay, so this is exactly this Rayleigh function here. Right, so this is exactly the function that we can put in here. So let's assume that we can find, given any a's and ai's and bi's, that I can find what the equivalent a tildes and p tildes are. We'll see that this is very simple. Okay, so let's assume that it has this form. Then how can we implement this with respect, how can we bring this in this form? What's the correspondence? Right, so let's look at one such term here. What does one such term correspond to? Where should I write the ai's, the ai tilde, bi tilde, where should they be?
The ai would represent the weight.
Okay, which weights?
Between, I suppose, the first and the second pair.
So first is which one?
So
This is first, this is first,
no, yeah,
this is first?
between this one and the center.
So let's call this, so typically we call this layer 0, we call this layer 1, and this would be layer 2. So just 2. So between which two layers?
For me, if it's the weight, then A1 is the weight between 0 and 1.
So let's check, right? So where's this function? This is the function that's applied. Where's this function applied? Right, this function is applied here. Right, you first take the sum. In this case, it's trivial because there's only one input. You add to it the bias term. Then you apply the function, right? And then you still sum it up. Okay, so this means that the ai tilde here, they actually correspond to this thing here, right? Because this is after the output of each of such node in the hidden layer, and then you still take the ai tilde and apply this. Okay? Now, where are the bi's, bi tilde? Where do they sit? They're suggestively named bi tilde. Right? So they're obviously the bias terms, right? So we have just the x. So all the weights here are trivially just 1, right? Then we have here the minus bi tilde, right? We add here the bias term, whatever that is, right? Then, so now we have the x. We add to it the bias term. Now we apply the Rayleigh function, and then we add everything up, right? So once we can bring this into this form, it's clear that we can represent that with this network. So the question now is exactly what's the relationship between these tildes and the not ones, okay? So let's check. Let's look at this picture here, right? And so let's look at the first one here, right? So the first one here is simply a line, right? In this interval between R0 and R1, all I have here is a line, right? That's the representation. And this actually corresponds to this term here. Okay, so this term here is supposed to represent that first part, right? There you see here, what will happen here, right? So when the x is smaller than bi tilde, since I have a plus, this will vanish. Okay? So what do you think the bi tildes will be with respect to the parameters that you have in this picture? The idea will be that each of those things has something to do with exactly one of these partitions here. Right? That's what we want to map. So what should the bi tilde be? Yeah, we have very few choices, okay? It's a good chance you get it right if you just randomly guess. Someone, please. Yes, oh, thanks. Sorry. Okay, it's a good guess. It's unfortunately not exactly like this, but okay, so it could be maybe the height. It could have something to do with this thing. It's not quite this, so, but okay, you know, you have to see. So again, what I want is that this represents the first interval. So this means that better, all this thing vanishes in the first interval. Okay, this better be 0 in the first interval. Okay, so what happens is that the bi tilde are equal to the ri, right? Or actually ri, I guess it's ri minus 1. So let's assume we didn't have this, and let's just look at the first interval. Okay, in the first interval, assume this is not here. In the first interval, I want this to match this here. Right? So it better be that the slope, the A1 tilde is better what? What is the slope here? A1. A1. Okay, so we better have that A1 tilde is A1. Okay? And so for the first one, you're right. Okay, so for the very first one, what is the B1? Well, if this is a shift, right? The very first one, the B1 tilde, better be this one here, right? Which is exactly, of course, the same thing that the B1 plays here, okay? So it means the B1 tilde is better the B1. Okay, so this represents the first slope. Now we are arriving at this point here, right? We are arriving at this point here. Now at this point here, since we set the B2 tilde, right? So B2 tilde, so in particular this means that B2 tilde is R1, right? Now since we set B2 tilde to be R1, it means as soon as x is bigger than R1, so it means it's now in the second interval, we still have this doesn't go away, but we have in addition this term here, the first term here, right? So it means now what we want is the following. We still have this representation here. This doesn't go away. But what we actually want is this representation here, right? We want a different slope. So how can we get this different slope? I have this slope because that's just the initial thing, right? This doesn't go away. But I want this slope. So how can I change the slope by adding something? What should I set the A2? This is the slope, right? So A2 tilde should be what? The slope I want is A2, right? Yes.
Second slope minus the first slope.
Perfect, right? So the slope I want is A2. What I want is the slope A2, right? But I have already slope A1, right? So I better, whatever I add now, okay, better is that whatever I have, so what I need is that this plus A1 better be equal, I have the sign wrong, so A2 plus, yes, okay, so what I have is, I want slope A2, I have already slope A1, I can add a slope to it, okay, and the sum of the two better be this thing here, right? But so now note, what is A1? A1 is the same thing as A1 tilde, okay, so this means that A2 is equal to A1 tilde plus A2 tilde. Okay, so that's my relationship. So good. So now we start having two functions, right? We have this function plus we add to it another function. I guess the other function would look something like whatever. You know, we add some slope down here so that the sum of the two things will give me. I guess that's too much, right? So maybe well, it has to be a little bit down. So we add to it, and there's no shift, right? So we add to it basically here this extra function here, like some extra function here, right, which has this downward slope. So I add this to this, and I get that. Right? So now I have achieved this function here. Right? So now I have this function here. So now I get to, so this was R1. Now I get to R2, right? I get to R2, and I have the same issue here, right? Really what I want is now that I want the slope to be equal to the slope A3, right? Clear? But what I have is a different slope, right? And so if you work this out, you will see that the general thing is that this should be, the relationship should be this. Okay, so generically, you have to set the parameter AI to be equal to the AJ, J is 1 to I tilde. Okay, so if you do that, you will see that this representation, if you set the parameter here, will go into this representation here, and this is just a different way of writing the same thing. More or less clear? Okay. You might wonder here a little bit, okay, why? Because if you look here, right, we have here essentially 3 parameters, right? We're having AI, BI, and RI. Clear? And you might be slightly worried how this can be that we can write it here, because here we have only AI and BI. Is that clear? How is it possible that you can write something that has 3m parameters as something that has only 2m parameters? Any explanation? The point is that this function is continuous, right? And so there are not really 3 parameters. Why? Because at every intersection, this thing and this thing have to agree at that point here. Is that clear? Right? So what you have is that you have that AI, let's say, RI plus BI must be equal to AI plus 1 RI plus BI plus 1. Right? You must have that these lines here that you describe, in order for this to give a continuous function, they must agree always at the intersection points, right? And because of that, you get for each of these intersection points 1 equation. And so effectively, you don't have 3 degrees of freedom per section, but you have only 2. Does it make you feel better, worse, equal? Okay? Good. So, as we have seen, you can write it in this form. And once we can write it in this form, it's clear that we can represent it as a standard linear, standard neural network with one single hidden layer. Okay? And we need exactly as many nodes in this hidden single layer as we need line segments in the approximation. Okay, but now we have something, whereas the previous derivation that we did was kind of, approximate, was like a graphical one. This is actually rigorous. Okay, it's rigorous, but it still has the same problem that we had with the other one, in the sense that this doesn't tell me how many such line segments I need. Okay, it's still not nearly as powerful as the theorem that I stated to you in the very beginning. Okay, so summary, enough with this. Okay, so the first part, neural networks, and there are many other such theorems, are quite powerful. Okay, right now, even just a single layer can approximate pretty much any reasonable function, and then you still have all the degrees of many layers. You can still have different, network, different activation functions and things and so on. So clearly, they can represent a very broad class of functions. That's not an issue. So now what we need to worry is about how do we actually learn these parameters, right? All we know is that in principle, there's a function there, but we don't know if we can actually learn it in any reasonable, efficient way. And so let's talk about 2 things. So let's maybe talk about the last 15 minutes of the first hour, first of some degree of freedom that we have. And in the second one, we'll talk then about the training. So So what is some degree of freedom we have? There are quite a few right now. Let's just talk about the degree of freedom that we have by choosing different activation functions. And then next Tuesday, we'll talk about some other degrees of freedom you have in terms of the structure of the graph and in terms of the connectivity. So we already, this is quite easy. We already talked about, right? We talked about the sigmoid. And so this just looks like this, right? And so that's a popular one. It's nice, smooth, differential everywhere, has many nice properties. Doesn't go down, of course, okay, stays constant here. But it does have a problem. And the biggest problem it has is that in training, and we'll see this, and hopefully I've looked already that during the exercise, these derivatives become very close to 0. And as we'll see in the training phase, when we compute the derivatives, there will be products of such derivatives coming in here. And if you have a product of many terms, each of them being potentially close to 0, you get something that's very close to 0, and that can cause trouble in the training phase. Okay, so there's tangent hyperbolicus, which is essentially the same, but now you just, it just goes from -1 to 1, so it's kind of symmetric, but otherwise it's essentially just a shift in the scale. It's not really much difference. We have ReLU, right, and we already saw what this looks like. This function here, and so this is the function just. Sometimes we write it as x plus, or we write it as the max of 0 and x. And so this is something that's actually quite often used, seems to be working quite well. One of the nice properties is that at least in the positive part here, you have that the derivative doesn't change, it's always 1, and so you don't have this vanishing gradient problem, at least in this part. You still have it here, okay? So sometimes you can do small versions. So for example, there's a leaky ReLU. And leaky ReLU is essentially ReLU, except that you also build in a small slope. So this is the same slope here. This is a slope 1. And then you build a small slope. Okay, so this would be the function max of alpha, x, and x. And alpha would be some very small positive number. Okay, so alpha small. Right, and so this alpha would just make sure that even in the negative part, you don't have a derivative that's 0, but it would be significantly smaller than 1. Okay, so that's another version. And there are many, many other ones. I think ones I have still in the note is called max out. Max out is kind of a little bit like a generalization of this. So what you have in there is again, you have the max. And now you simply take the max of several linear functions. Okay, so you simply, so the idea is basically like this. So think of this node here, right? Then what do? You typically take a weighted sum of these inputs here, add a bias term, right? And then you would apply the nonlinearity, right? So now what we do is the following. We're taking several linear combinations with several different bias terms, and then taking the max of that. Okay, so this, let's see how can I write it down. So it has kind of the form. So this x is now, think of this x now here as being a vector. So then we can write it as something w maybe 1 transpose x plus b1, and maybe w2 transpose x plus B2, and you could have several other ones. Okay, so each of them, so these are the weights, these are all vectors here. These are the weights for one of the linear combinations, and then you add a bias term to it, and then you take another linear combination and you add some bias term to it, and maybe you take a third one, right? And then you take the max of these functions. Okay, so again, it's linear inside, and then you just take the max, and that makes it nonlinear. Okay, and in the notes you have some different representations for this. Okay, there are many, many other ones. Okay, so there's quite some degree of freedom. Some of the most popular one is clearly, and that works the best, is probably ReLU. Okay, that you see quite often. Any questions? Okay, so if there are no questions, then let's get to the main part, and that's training. So we have training. Now, the good news is that the way we train it is, the algorithm that we have used since the very beginning, stochastic gradient descent. And so in that sense, there's absolutely nothing to be said about it, okay? You all know how it works. You have the cost function, you have parameters in there, you are at a certain state, right? You have you're already somewhere, you have already some parameters that you have. You compute the gradient, you have a small step size, you walk a little bit in the opposite direction of the gradient. You have a new state, a new set of parameters. You compute again the gradient at that point, and that way you're trying to minimize the cost function. Clear? Okay, so in that sense, there's actually absolutely nothing new that we said. It's exactly the same that we have always done. The only difference is that because neural networks have this really nice layered structure, rather than computing the gradient or these derivatives with respect to each of these parameters essentially one by one, which could be quite costly. So such neural nets, if you have hundreds of layers and thousands of nodes in each direction, and we know even that if you take a fully connected one, if I have k in each direction, the number of parameters is k squared. So we have something like k squared times L parameters in there, and that can easily be millions. So this could be quite costly if you had to compute the derivative with respect to this. It turns out that by something that's called backpropagation, for those of you who have done communication, very similar to something like a Viterbi algorithm or dynamic programming, something that hopefully many of you have seen already, simply by structuring the computation in a nice way, we can do all the computation by once going from the graph left to right, so from input to the output. That's called the forward pass, and then doing a backward pass and going once from the output back to the input. And so essentially the amount of computation we have to do is we have to touch, essentially every edge we have to touch and do a computation for every edge. Okay, so it's roughly the number of edges have, that's the computational complexity. Okay, so that's significantly better. So we can structure it that essentially we can reuse computation for computing one derivative and reuse them many times so that it's much more efficient. Okay, so the only thing, the only point about talking about this is to go over this algorithm and to see why we can do it more efficiently. Okay, so the point is to talk about what's called backpropagation. And so the only point is computational efficiency. There's no new algorithm that you learn per se. It's just a way to come to efficiently do it. So in order to do this, the challenge is to have a nice picture, because otherwise we're going to go crazy. So again, we have layer x0. We have the layer here, right? We have x1 here, or layer 1, and then generically we have here xl, we have here xl plus 1, and then at the end we have here the layer x capital L until we go to the output here, and that will be my xl plus 1. Okay, so this here is the input. And then remember how this worked. We go from the input towards the output by a forward network. And so the way it will work, I will not do all these things. The way it will work is that I have now, since I have a fully connected network, I have now for every node here, let's assume this is the node J, then I have from any node at layer L a connection to a node at layer L plus 1, and there's a weight here, right? And the weight is W. It's L plus 1, and this goes from I to J, right? So remember that's how it went. And then of course, I have here still a bias term. So there was here a B L plus 1 J. And so if I'm looking here at the output, right, then I get here the output xl plus 1 J. So the output that comes up here, right, was equal to, let's write this down again, was equal to the sum. So collecting everything over I is 1 to k. I look at the input at the previous layer, I multiply it with the weight that goes from I to J. I add to it the bias term, and then I apply the nonlinearity to it, right? So this is how I got from one layer to the next. Okay? Good. So now the only thing that we still need to specify if we want to do training is, so far we only described kind of the function that we have. So this whole thing, let's say from here to here, describes some function. Okay, so we'll describe, so this thing here will simply be f of some x0. The whole thing will just be some function that we describe, right? Now, the question is still, what do we do with this whole function? So we need some task. And so, it's not going to be super important. The algorithm doesn't depend on exactly what the task is. But just to be specific, let's assume that my cost function is that what I do is I just take the least, I have to take like a least square. So I have the yn, I have yn minus f of x0 n squared. Okay, so let's assume that the cost function here is that I wanted to do regression, okay? And I just take the square, the L2 norm as my metric here, just to be specific, okay? If this was something different, we'll see that the computation essentially doesn't depend on it. There's only one initialization that we have to do that depends on what exactly this function is, okay? And if this was something different, it would be trivial to change the whole computation, okay? So this is not the major point. Okay, so far so good? So now, what is it, right? We want to minimize. So this cost function, of course, depends on that function f, and this function f depends on all these parameters, right? We said that we have roughly something of order k squared times L parameters in their order, right? Because we have every such transition here, it goes between k and k. We have fully connected their k squared weights, and we're having L such length. So it's of order k squared times L parameter. And then there's a factor, whatever, because I have all the weights and so on, but just order, right? So there are a lot of these parameters in there. So what do we want to do, right? What we want to do is we want to compute the gradient of this cost function, right? With respect to each, or the derivative of cosine with respect to each of these parameters here, right? The gradient with respect to this whole vector of parameters. And the way we will do it is we'll consider stochastic gradient descent. So it means right now, when we do this, we'll just focus on one term here. Okay, so we assume that I pick one sample. So I pick one yn and xn here, right? And then look at this term. So I forget about this sum right now. And then for that term, I compute this derivative. Is this clear? So what will happen is, since we do stochastic gradient descent, so we pick one sample, right? And so the sample will be yn or xn. And I write here 0 just to make it clear because it will have several zeros, several x's around, and yn. I pick one such sample. Then I have this cost function here. And this will just depend now on, let me just write here n, okay? So there's no sum, right? Just the nth term. I'm just looking at one of the terms in here. Okay, I'm doing stochastic gradient descent. And now what I need to do is I need to compute, okay, I need the gradient. So this means I need to compute the partial derivative of FL, Ln, with respect to each of these weight terms. Right? And the same thing, this, with respect to each of these bias terms. Right? And when I write each, it means I have to go over all L, over all I, and over all J. That's what I have to do. Right? And once I have it, I get a large vector. I walk a little bit in the opposite direction of this vector, update my, my state, okay, my weights, and then go on. Clear what we have to do? Okay, and we take a break, and when we come back, we'll see how we do it.